Hey everybody, I wanted to take a little bit of time to talk about refractive index, or sometimes we reverse those two words and call it index of refraction. But this is a laboratory technique that we use pretty often, and it's pretty easy to use. And I think it's important for us to spend just a little bit of time talking about what it is and what it means. Some of the nitty gritty of refractive index is really, it's a ratio. We know that light travels at a certain speed in a vacuum in space, 3.0 times 10 to the 8th meters per second, 300 million meters per second. But what we also know is that when things get in the way of light traveling, like windows and liquids and things like that, that light slows down. And that creates a phenomenon that we know as refraction. And so the refractive index is basically a ratio that compares the speed of light in a vacuum to the speed of light through a certain liquid. And so you can see that in the couple of pictures, the result of refraction. So the straws here that I'll highlight, the reason why it looks discontinuous is because of light refracting through the glass. Okay, and here the light's playing a really big trick on you, because not only is it refracting through the glass, but the glass is curved, and that creates all sorts of weird tricks. And this is actually a lab demo that takes refractive index into account. Is that it turns out that glass has a very similar refractive index as olive oil, and you can do this right at home. And so if you fill a container with olive oil, and then fill a smaller container, you can see the beaker in the middle here with olive oil, you actually can't see the container inside the larger beaker, because they're both refracting light at the same amount. So you give that a shot if you want. It's kind of neat, or you can go look for a video online about it. But regardless, every liquid does have a refractive index that is listed. For example, water has a refractive index of 1.33. You may want to write that down. It's going to come up later. Ethanol has a refractive index of 1.36, and olive oil, in our little example here, has a refractive index around 1.4. So every liquid has a refractive index, and we can record it, and we know pretty well. We can even Google refractive indexes pretty easily. But refractive index definitely has a dependence on temperature. If you think about light traveling through a liquid, and the reason why it gets slowed down is because those liquid molecules are getting in the way of the photons. It's not like it slows it down a ton, but at least it slows it down enough. Temperature affects density, right? The more dense something is, the closer together the particles are, and that prevents particles of light from traveling as quickly through them. So it stands to reason that temperature is a factor when determining index of refraction. So you can see in these two graphs that it's an inverse relationship, that as temperature increases, index of refraction decreases. And again, from a scientific point of view, that makes sense. As the molecules speed up and get further apart, they're getting less in the way of the light that's traveling through them, and causes the refractive index to get smaller. So here's a couple of examples. So this is water, and again, you can see that the refractive index of water is about 1.33 from the previous slide that I had. But as the water gets warmer, the refractive index definitely goes down. And the same is true with silicone oil. It's an inverse relationship. The warmer something gets, the higher the temperature, the lower the refractive index. So this is important, because when you go look up the refractive index, we need to have a standard temperature that we look at refractive index for. So that standard temperature is always going to be 20 degrees. So you'll see that reference temperature used all the time. So 20 degrees is really where we want to make sure we have our reference data. Now, you'll notice that for something like water, that the refractive index isn't changing by a ton over, I guess this is an 80-degree range, but it's changing enough that we have to be careful of it. Okay, so the other thing that I want to talk about is when you mix liquids. Now, this is the best graphic I could find that shows this. So we're going to ignore this this black line because that's an indication of density, but we're going to look at this blue line here. So what this is, it's a mixture of ethanol and water. Okay, and this on here, the x-axis down here is the mass fraction of water, and so at 0, when we have 0 water and it's 100% ethanol, well, what did we say the index of refraction of ethanol was? 1.36. Perfect. And that's what this data table shows. It's an index of refraction of 1.36. And what did we say the index of refraction was of pure water? Here we have water. If the mass fraction is 1.0, it's 100% water, then the index of refraction is 1.33. And that's pretty good. But notice here that as the mixture changes from 100% ethanol to going toward more and more water, that the index of refraction changes. And in general, okay, this is in general. I know that this graph is a little bit wonky, but in general, that relationship is pretty linear with the exception of this first 20%, okay, of the mixture. Okay, so you can see as we go down through here, we can predict pretty accurately what the percentage of the mixture would be based on the index of refraction. The long and the short of this is that if you have a pure compound, like let's say we had pure water, and then we had a sample that was contaminated with just a little bit of ethanol, we could see that in the refractive index data. Okay, you could see how the pure compound was impure by the ethanol based on the data. So what does this all mean for you? Well, there's a couple of things that you can get from index of refraction. Actually, even though it's a very simple instrument to use, you can actually get two types of things from this, which you can't from the more expensive sorts of things in the lab. The first thing you can do is identify the compound. If you know what compound you're trying to make, and the index of refraction is very close to that literature value, then you know that you probably made the compound that you were trying to make. You just compare the two indexes of refraction, the experimental versus the literature. If they're close, then hey, you probably did a pretty good job making that compound. But the other thing that you can do is also determine the purity. Okay, because the relationship is, I'll say, quasi-linear, you can say that the further from the literature value that your index of refraction is, the less pure your compound is. And that's a pretty powerful statement right there. If you have a value that is the further away the literature value, the further away from the literature value your experimental data is, the less pure your compound is, and it's a fairly linear relationship. The other thing that you can know is that the index of refraction is going to fall in between the values of your impurity and of your target compound. So that just means that you can pretty much identify what the impurity will be based on what compounds you're using in the reaction, because there could be some reactants in in the mixture, and also based on what side reactions you get. So you can also make some educated guesses as to what those impurities would be. So whenever you're using index of refraction, the expectation would be that you would be able to use that data to both identify your compound and to use that data to make some sort of comment on how pure your compound is and what maybe the impurities are. So there you have it. That's index of refraction in a nutshell, and have a great day.